If people have questions on the camera, they're gonna be able to stop me.
Yes, they will, and I'll if they write it on chat, I'll just forward it.
Okay.
Okay, it's 2:30. So hello everyone, and a warm welcome to the final installment of this year's Distinguished Theme Seminar Series. The series is organized by the Department of Statistics at Purdue University. This year's theme is Recent Advances in Statistical Inference. A big shout out to the theme seminar committee for organizing this series. My name is Ankit Chakraborty. I'm an assistant professor in the department. Before we begin the seminar, we would like to remind our audiences of a few things. So this seminar is being live streamed on our department's YouTube channel. The URL is www.youtube.com/c/Purdue University Statistics. People who are joining in from Zoom, please keep your microphones muted at all times unless you are actively asking a question. If you are watching on YouTube, you can submit any questions you have in the chat and we will forward them to the speaker. Graduate students, please remember to attend the student interaction session with Professor Barber at MAP 215, starting from around 3:40 to 4:15 p.m. Today, it is my pleasure to introduce our speaker, Professor Rina Barber from University of Chicago. Rina Barber is the Louis Bloch Professor of Statistics at the University of Chicago. Her research interests focuses on problems in distribution-free inference, multiple testing, sparse and low-rank methods, and medical imaging. She received an MS in mathematics in 2009 and a PhD in statistics in 2012 from University of Chicago and was a postdoctoral research fellow at Stanford University in 2012 to 13 before joining the faculty at the University of Chicago in 2014. She is the recipient of a Flow On Research Fellowship in 2016, NSF Career Award in 2018, and the Tweedy New Researcher Award in 2017, Peter Kelvin Hall IMS Early Career Prize in 2020, and also the COPS President's Award in 2020. Today, Professor Barber is going to talk about conformal prediction beyond exchangeability. We are honored to have Professor Barber here with us. So let's give her our full attention.
Thank you so much. Thank you so much for the intro and the invitation. I think it's amazing what you guys are doing with a series with the theme, and I'm really happy to get to be a part of it. So thanks so much to everyone who came and to everyone who came on Zoom. And please feel free to jump in anytime with questions, whether on Zoom or in person. I'm very happy to answer questions. In particular, this work is new and a lot of these ideas are still under development. So your questions and feedback will help us a lot. Oh, sorry, let me see, I can figure out the arrows. Is it just the mouse? Okay, it's just the mouse, got it. Great, all right. So I'm really lucky to work with great collaborators on this work. So the work that I'll be presenting today is a project joint with my long-term collaborators, Emmanuel Candez, who I also did a postdoc with, Aditya Ramdas and Ryan Tibshirani. I've been really lucky to get to work with them. And in particular, I know that Emmanuel gave a talk here a few weeks ago in this series. So the work that I'll be talking about today is complementary to what he talked about. I know he talked about a lot of projects in conformal prediction and distribution-free prediction, figuring out how to deploy it in lots of really complex and challenging settings. Today, I'll be talking about our joint work, looking at one more setting, which is what can we do moving a little bit beyond the framework of this type of methodology, which is the framework of data exchangeability. So I know for many of you, this framework's already familiar from his talk, but I'll try not to spend too long on the intro, but still want to start from the beginning so that we're all on the same page. So I'm going to be talking only about predictive inference today. And so predictive inference is the problem of basically saying, here's my fitted model, how well is it actually doing? So how do I quantify my uncertainty around the predictions that I am handing to you based on the training data that I saw? And in particular, we know that this is something that we can't just do naively. If we run some kind of regression algorithm on training data, then even ignoring the issue of whether our training sample is representative of future data that we want to be able to predict accurately, even if they're all from exactly the same distribution, we still know that there's an overfitting problem, meaning that however well my trained model is doing on the data that I trained it on, it's probably not going to do as well in future on data that it did not see during training time. And so fundamentally, the problem of predictive inference is kind of to address that, and at the same time, to also understand whether it's possible to be robust to other issues, like maybe the training data isn't perfectly representative of test data. So in my intro, I'm going to talk about the field of conformal prediction and how it's looked at this problem when we do assume that the training and test data are from the same distribution, but we have no reliable model assumptions and we're worried about overfitting. But the goal of the work that I'll be presenting today is to also move forward in the second direction, which is to understand what we can do if the training data isn't just sort of IID from the same distribution that I'm going to be trying to predict on for my target. Okay, so what do we actually normally do when we run whatever our favorite algorithm is, whether it's least squares or sort of cutting edge machine learning stuff, whatever it is that we run, we then output a prediction. What do we do to try to say how accurate that prediction is? So one of the most common things to do is to say, my prediction is within plus or minus some margin of error from the truth most of the time. So we give prediction intervals that are something like mu hat of my new value of x. So here mu hat is whatever the model it is, whatever predictive function I trained on my training data. The subscript n reminds us that we trained on a sample of size n. And xn plus 1 is whatever is the x value for the next point that I'm trying to predict y for. So xn plus 1 is the features that I can see, and now my job is to predict its corresponding value of y, its label. So if mu hat of x is my predicted value, how do I say like plus or minus what margin of error? So we already know, of course, if we just use the residuals from the data that the model was trained on, those are too small because of the overfitting problem. But on the other hand, how do I know how much bigger to make it? So if I have some kind of parametric model, like linear regression, and I actually believe that that model is correct, we have formulas that tell us how wide to make this margin of error in order to compensate for the overfitting problem. Now, of course, I might not believe my parametric model, but maybe I'm willing to make some non-parametric assumptions, like maybe my data comes from a distribution with some kind of smoothness property. If I make those types of assumptions, again, I can use some kind of formula or existing tools to tell me how wide to make that margin of error. If I really don't want to rely on any of those assumptions, perhaps I want to use something that has more of a model-free flavor, like cross-validation. So let's say I fit my model, but I leave out a portion of my training data, and then I see how big were my errors on that left out portion, and then I cycle through and do cross-validation. So it's really only this last option that has the flavor of being model-free without really relying on untestable assumptions in the data in order to give me a margin of error that's guaranteed to be wide enough that I really do tell you an accurate predictive interval, maybe like 90% of the time. Sorry, let me pause a second. Is there a way to turn off that noise? Is that coming from Zoom?
The thing is that if we turn this off, then
Okay.
yeah,
Is
then
it possible to turn off that sound?
yeah, I'll sort of lower the volume because if they ask a question, then we can't.
Isn't there the join and leave sound?
It's like yeah, join and leave sound. Yeah.
Yeah. It's, I don't know if this is the same version of Zoom, and mine is under participants. If you click participants.
You can turn it on again.
Here.
Participants, yeah, click that. Sorry, click participants, yeah. And then there should be options.
So
Oh,
actually
mine
they are-
looks different. Okay, maybe.
They are
mine
actually
does look
joining in
different.
another link. So
Oh, I see.
there.
Okay, well,
So
I'm
maybe
sorry if it's bothering anyone,
no,
but
no.
I guess not worth
Yeah, it is
doing
bothering
anything about it. Okay.
Yeah.
Sorry to interrupt.
Yeah, no, that's fine. No, people are joining in another link altogether, and the mail is coming to my.
I think you just turn on the volume now.
Yes, that's what I did.
Okay,
That's what.
sorry to interrupt. I didn't think it would be complicated.
The Outlook is open over there. Yeah, you can.
Should do.
Great, thank you.
Hopefully this will work.
You want to just turn it off.
Awesome.
Turn it
Okay.
on off.
The volume off?
Yeah. See if it works.
Yeah, I
think we
closed Outlook altogether, so
Yeah.
we should not have any more issues.
great. All right, thank you so much. Sorry about that. Okay. Okay, so when we construct a prediction interval, what are our goals? So basically, as in any stats problem, we're always trading off between two things or sometimes more things. So in this case, fundamentally, it's two things. We want validity. So we want to say that when I give you a prediction interval, so like given your X value, your features, then your Y value that you haven't observed yet is going to lie between this and this, these bounds. Is that statement actually accurate with some desired probability? So that's validity. And we'll talk a little bit more about sort of what that validity means, like what's that probability taken with respect to. But the second thing, of course, is we want some kind of efficiency or precision, because one way to be valid is to say that your output Y will be between minus infinity and plus infinity, but obviously that's not useful. So coming from a more classical stats training, to me, it's useful to think of this as analogous to type 1 error versus power. So the validity is kind of playing the role of type 1 error here. The precision is playing the role of power. And roughly speaking, the methods we're going to be talking about are going to worry mostly about the first thing. And then how precise are you able to get is largely a function of like which algorithm or which model fitting procedure do you pair our methods with. So I won't be talking about the second one much, but of course we want to bear in mind that these methods are only useful if they can do well on both of these criteria simultaneously. Okay. So now using a holdout set is probably like the most standard and well-known thing to do to try to avoid the overfitting problem. So what does this look like and what guarantees does this give us? Does it use any assumptions? So for a holdout method, you would split your data. Let's say we split it in half, although of course that's not necessarily the optimal proportion. And we're going to use one portion of the data, so data points 1 through n over 2, to run our regression. Again, that could be something parametric, that could be something very modern, or anything in between. And then on the holdout set, we're going to compute our errors. So in this case, I'm just computing error as the absolute value of the residual. Again, that's one specific way to do it. I'll come back to a generalization shortly. And then finally, the prediction interval is to say that I'm going to give you the prediction that was fitted on the first half of my data, my training data, but I'm going to expand it into plus or minus the margin of error, where the margin of error was calculated on the second half of my training data. And as a result, I don't have the overfitting problem, because the margin of error was calculated on data which was not used in training. Now, of course, this type of method has been around for a long time, but what is it exactly doing? And in particular, can we rely on it if n is not very big? And so that's something that distribution free inference can use as a starting point. Yeah.
So does the margin of error depend on X?
That's a really good point. Does the margin of error depend on X? So in this most basic construction, it does not depend on X. And of course, that doesn't really make sense because we know that not all data has, equal variance at any point in X in feature space. So one thing to point out is that the validity guarantee right here, it only says it has to be accurate, let's say 90% of the time, but it could mean that it's 95% accurate for some X's and only 70% accurate for other X's. And so the construction of not depending on X is obviously not optimal, but it doesn't actually contradict this goal because this goal right now is so weak. In practice, you would want to refine the construction a lot in order to depend on X better. And I don't want to get too much ahead of myself here, but I'll just mention that basically the idea is that score of like how well did you predict the ith point, you can make that score locally rescaled. And as a result, then the margin of error would be working on sort of like a rescaled metric, which is how much wider do I have to make it relative to my estimate of variance at X, rather than having it be the same for every X.
Yeah.
So I agree that right now this is like a super naive
but
start.
Going back to the original question, over here you're targeting the mean more or less.
So this is just one example, yeah.
Yeah, but if you instead work on a quantile regression, then if you estimate the quantile is differently, then it's no longer a problem.
That's right, yeah. So using quantiles as your base procedure around which you build a prediction interval wouldn't take the form quantile plus or minus a fixed margin of error. It might be something like from what estimated quantile to what estimated quantile do I need to be? And so that's like a more sophisticated choice of what you plug into this general recipe. So I'll come back to those generalizations in a minute. Thanks for pointing that out. Other questions? Okay, with that in mind, the question really is like, one, what can we say about the holdout method or related versions of that method that use more sophisticated procedures? What can we say about it? Is it implicitly using assumptions? Is it only going to be valid if n is really large? Or can we say something stronger? And then at the same time, holdout methods remove overfitting, but they introduce the problem of losing some of your sample size. So is that avoidable as well? And with those questions in mind, I want to introduce some background on the framework of conformal prediction. So the key idea of this literature is that you can do a ton of statistical inference using only one assumption, which is the assumption that data is exchangeable. So for example, my training data and my future points I'm trying to predict are all IID from the same distribution. So to give sort of the 1-minute background on this field, this was developed and introduced starting in the late 90s by Vladimir Vovk and collaborators. The definitive reference is Vovk et al.'s textbook in 2005, Algorithmic Learning in a Random World. And more recently, starting around 10 years ago, Jing Lei, Larry Wasserman, and their colleagues at Carnegie Mellon began working on conformal prediction and developing a lot of methods within this framework for statistical problems. So it's their work that first introduced me to this field. And I particularly want to mention this Lei et al. Paper in 2018, Distribution-Free Predictive Inference for Regression, which is a great introduction to this field. Okay, so the holdout method in the conformal community is often called split conformal prediction. And now this formula is going to look exactly the same as what we wrote down one slide ago, with one tiny modification, which is that when you compute your margin of error, again, using the simplest possible strategy of just having it be like constant margin of error across all x's, which not optimal, but just the starting point. When you compute it, instead of computing the 90th percentile, say, of your n/2 holdout points, you do something very slightly more conservative, which is instead of going up the list from smallest to largest until the position, which is like 90% times n/2, which is the length of the list, you instead do 90% times the length of the list plus 1. And that tiny correction makes basically no difference in practice, but it makes all the difference in the world in the theory. And Vovk et al.'s work proves that theoretically, with no constraints at all on the distribution, aside from just assuming exchangeable data, with no constraints on whether the model that you fitted at the center, mu hat, like mu hat plus or minus what, whether it's good or bad, and with no assumption of a large sample size, you automatically get the coverage level that you wanted, this 90% or 1 minus alpha coverage. So non-asymptotic, this holds at any finite n. And this comes straight out of exchangeability. So let's see why that's true and why we don't need n to be large, because it feels like we should, because we're using the holdout set draws of like how big is my error on the holdout set point. We're using that sample quantile to try to approximate the population quantile of like how well will I do on future test data. So it feels like we should need a large n. And the reason that we don't basically boils down to that tiny change in the definition of how do I calculate the sample quantile. So let's see why. So if the training data was not was separate from the holdout set, then that means that even after you train your model, the holdout points which I do have access to, and the test points which I don't have access to, they're all exchangeable with each other, or they're all IID from the same distribution as a special case. As a result, when I calculate the errors on the n/2 holdout points, so these ones right here, the residuals on the holdout points, and if I were to also calculate the residual on the test point, those n/2 plus 1 objects are all exchangeable with each other as well. If you have an exchangeable sequence of numbers, any one of them could appear in any order on the ranked list. So Rn plus 1, the one that corresponds to my prediction problem, the test point, it could be the smallest, it could be the largest, or anything in between with equal probability. As a result, this means that if I take the 90th percentile of the entire list, the holdout and test errors, then there's a 90% chance that my test error is less than or equal to that 90th percentile, because the list, you can think of it as like a random permutation of itself, basically. So this is equivalent to saying that if I only can see the holdout points and I calculate their sample quantile, but with the correction, so that's why this says Q hat rather than Q, then that event is the same thing, that the test point, which I no longer can see in my list, is upper bounded by the corrected 90th percentile of the list of holdout residuals. And then because of the construction of the prediction interval as like mu hat plus or minus this margin of error, that means that this is the same as the event of my prediction interval actually containing y. So we can see here that the +1, the correction in the definition of a holdout method, has to happen because instead of a list of n/2 holdout points, like in the middle pink line, I should actually be thinking about a list of n/2 + 1 exchangeable points, which combine the holdout data with the test data, like in the top pink line. Okay. So now what this tells us is that we don't have to worry about any assumptions or sample size requirements for holdout sets. However, holdout methods still have a sample size problem, which is that mu hat is not going to be as good when it's only fitted on half the data. And so my prediction interval is going to be valid, but it's going to be a little wider than optimal because I have to make it wider to compensate for errors in mu hat. So on the flip side, the naive method where I like maybe was not yet aware of overfitting, my predictive validity failed because my margin of error is too small. But the center of my interval, mu hat, that was fitted on the entire training data was actually more accurate. So we would like to get the best of both. And of course, it sounds like this is impossible. How could you have validity if you don't keep a holdout set? And so this is the insight of Vovk et al.'s work on conformal prediction, that you actually do not need to do a holdout method. Now, nothing in life is free, and the cost here is computational. But this still tells us that statistically, we don't have to face this trade-off. So this method has become known as the full conformal method, meaning I use the full data rather than splitting the data. And so its properties are that the models it uses are fitted on the entire training set, meaning you don't have a loss in sample size, and you still guarantee distribution-free valid coverage, but it's a high computational cost. So here's what the method looks like. In order to introduce it, let me first talk about something that you can't actually do. It's going to sound impractical because it involves a quantity that we cannot see, which is the target of prediction, ym + 1. Then we're going to see how what we did with ym + 1 can be repeated even if you cannot see ym + 1. Okay, so let's imagine that I could actually see the objects that I'm trying to predict. So I can see my untraining points, and also I can see the xy test point, xn + 1, yn + 1. And given that data, of course, I don't actually have a prediction problem, but let's pretend I still wanted to predict for some reason. And now I feed all of that data to my regression algorithm, whatever it might be. So here, curly A is just standing for any method that I use to start with a data set and output some fitted regression function mu hat that takes x and maps it to a predicted y. Okay. Now I do this, and then I compute my residuals for all of my training points and for my test points. And now we might wonder, do I have overfitting? So these residuals are overfitted in the sense that if I were to feed fresh data to my fitted model, it would probably have higher errors. But because in this hypothetical plan, I have fed my test point into the model at training time, the residual Rn + 1 for the test point is just as overfitted as the residuals on the training points number 1 through n for this particular fitted model. In other words, I do have overfitting, but overfitting applies to my test data as well as to my training data. So it's kind of all okay in the end. And then the last step is I'm going to see whether the residual on my test point is or isn't in the bottom 90% of all of my residuals. Now, because the data points were all used at training time, the test point error shouldn't be larger than all the training ones, except if that happens by random chance. Again, because overfitting applies to everything here. So as a result, this should have a 90% probability. Now I'm implicitly making two assumptions. First is that the data that I fed in is exchangeable. If it's not exchangeable, like if the training data has low variance and the test point has high variance, then even though they all got used at training, I still probably have a larger residual for the high variance point. But if the data is exchangeable, we should be okay. I'm also making a second assumption, which is that the algorithm treats its input symmetrically, meaning that the test point got given to it last, like in the order 1 through n + 1, but that doesn't matter. So something like least squares, something like any procedure that trains on your data as one batch, something like stochastic gradient descent that randomly shuffles the data, on average, sort of in a distributional sense, it treats the data exchangeably. So it can't be any algorithm that uses the ordering of the data. We'll come back to that point later because that's something we want to address with our new work. Okay, Now, of course, in practice, I can't see the value of y that I'm trying to predict by definition. So instead, I'm just going to plug in a guess, little y, and effectively, I'm just going to test the hypothesis of whether that is the value that I'm trying to predict. So what we know is that if it happens to be equal to the right value, so if my guess got it right, then this event that the test residual is in the bottom 90% of all the residuals, this event should have 90% probability. In other words, if I get my guess right, I should get a yes. But if I get my guess totally wrong, I might get a no when I test that inequality. And then finally, the prediction interval, which actually might not be an interval, it might be a set that's sort of a bunch of disjoint pieces. It's all values of y in the real line or in like whatever space you're in, for which this event holds, so for which that inequality holds. Okay, so Vogt-Goodall's result says that just like for split conformal, full conformal also has distribution-free prediction. Again, we assume only exchangeability of the data and symmetry of the algorithm. The algorithm treats the data symmetrically. It doesn't do different things depending on the order of the inputs. And in fact, split conformal is just a special case of this. If you kind of adjust the notation, we see that these two results are actually the same result. So again, this is just based on the argument from the previous page that if you were to have plugged in the right value of y, the event should have a 90% chance of holding. And so if you search for all values of y for which the event holds, probably that search will include the true value of y as one of the things you include into the prediction set. Okay, so we see that this has a huge computational cost, but statistically, we kind of have won on both counts. We were able to use the full training data for fitting the most accurate possible models, but also we still have distribution-free validity, just like you would get with a data splitting approach. Okay. Now, back to the question that was asked, which is why are we doing mu hat plus or minus a fixed margin of, or sorry, a constant non-x dependent margin of error? That's really not the thing that's best adapted to many realistic problems. So in this talk, I'm just using this, this measure of like what margin of error means. The absolute value of the residual is less than or equal to blank. I'm just using that as sort of a running example because it's the simplest construction. But conformal prediction can be constructed with any type of score, where the score measures how far from typical is this data point. So we could measure that by saying how far is y from its prediction mu hat of x. But of course, we could instead measure it in tons of different ways. So here's just some references of some of the most popular scores that have been developed recently, but there's plenty more. For example, conformalized quantile regression by both Romano et al. And a different version developed by Kivaronovich et al. These regression methods start with quantile regression and then do these adaptive intervals that might be much wider at some values of x than others. You can use distribution estimation, like you estimate the conditional distribution of y given x and work with that directly. You can develop scores that suit categorical y's rather than real valued y's, as we're talking about today. So this is really like one example that's only a drop in the ocean of what conformal can do. I'm going to continue using it as a running example, but I just want to highlight that this field is very flexible in terms of handling different types of data. Okay, and then last thing I want to mention before sort of in this intro is that full conformal and split conformal are kind of on opposite extremes of like efficient use of the data versus efficiency computationally. And there are methods such as cross-conformal, jackknife plus, and CV plus that are basically cross-validation style methods that fall somewhere in between the two. They use the data more efficiently than split conformal because they sort of cycle through different folds of the data. They cost computationally less than full conformal because full conformal in theory means that you have to search over every possible value of y and refit a model every time. For something like 10-fold cross-validation, you would only have to refit 10 models. So there's kind of these in-between versions of the method as well. Okay, so sorry, before I keep going, let me just pause here and ask if there's any questions on the background of the conformal framework. Okay, hopefully if there's Zoom questions, I'll hear you. All right. Yeah, that's a great question. So if your data is categorical, I didn't give any details, but there are scores. So here's a nice reference looking for some scores for categorical. But I want to point something out that's a little more fundamental than what score do you use, is actually, would you even be able to ask for a prediction problem? So if you're in a situation where there's many possible categories, predictive inference makes a lot of sense because it could be that I'm going to narrow it down to like these 5 possibilities. So I don't know if this photo is like of a, house cat or a lion, but it's definitely not a car, right? But if you only have 2 labels, like did the person get the disease or did they not, even an oracle that knows exactly what your probability of getting a disease is, the prediction set would often have to contain both categories. Because unless it's a disease that's almost deterministic, like based on genetics or something, for most people, if their chance of the disease is not like 1% and not 99%, but somewhere in between, the only valid prediction interval is the prediction interval that contains both yes and no in its answers. And so for binary situations, predictive inference is not always a meaningful problem. But for categorical problems where there's tons of categories, and even if I cannot tell you it's this one, just narrowing it down is actually like a useful inference tool to have. In that case, there's lots of really useful scores that basically start by, instead of fitting mu hat, fitting p hat, which is like, what's the predicted probability that this is a lion given the image? And then your prediction set would be like, for example, it could be any label whose p hat value is at least 10% or something of that form. Yeah.
As a follow-up, how do you determine the threshold that you have 10%?
So, sorry, one sec. So if your margin of error is defined by the residual, you take the sample corrected quantile of the residuals and you look for basically any y whose residual is no larger than that, right? And so the analog holds for anything else. You're looking at a sample quantile of the scoring process as applied to the holdout data. The full conformal version is kind of analogous. Yeah.
I just have a part-time question. I just want to confirm that X1 to Xn are nowhere seem to be independent.
So they can be exchangeable rather than IID. So exchangeability is basically like the one relaxation beyond IID. But this is not treating the x's as fixed. So this is not the same as like a classical regression setup where you think of the x's as fixed and then the y's are random. Here, the entire XY data point is either coming IID from some process or the data might be exchangeable rather than IID.
No requirement of independence, just exchangeable.
Just exchangeable, yeah. Yeah.
Related to that question, if I understand it correctly, if with this conformal framework, I can choose my favorite regression.
That's right, yes.
Can I assume IID within those models?
That's a great question. So one thing I really like about conformal is it doesn't say that you can only use tools that are model free. You're welcome to use a tool that assumes a linear model. The validity is not affected. So basically the idea is that, like, let's say for split conformal, let's say I assume a linear model for fitting mu hat, but I was slightly wrong. And so then my holdout set will correct the width of the margin of error in order to make my predictions valid anyway. So to me, it's like the best of both worlds. If you have assumptions that are like true-ish in the sense that they help you build a nice mu hat that does a good job predicting, but they're not true enough for me to use parametric methods to tell me how accurate are my predictions, you can still use assumptions for building mu hat, and then the prediction interval is built around mu hat in an assumption-free way. Other questions? Okay. All right. So everything we've seen so far, full and split conformal, as we've gone into detail, and the other methods in between that I mentioned, like cross-conformal, the cross-validation style methods, all of those depend on these exchangeability and symmetry conditions that appear in 2 completely distinct ways. One is the data has to be exchangeable. The second is the algorithm has to treat the data symmetrically or exchangeably. So this means I can't have autoregressive data. Also, I cannot use an autoregressive model. So those are 2 separate things. The data, where the data came from and what tools I applied to the data that I'm now going to build my prediction intervals around. So why do I need those things? And why do I need both of those things? It's because when I run full conformal, I need to know that after applying my algorithm to all of my data, meaning the training data and hypothetically the test point, if I imagine that I could see it, that after that, the residuals are exchangeable. So in order for that to happen, If I want to get exchangeable residuals out, I need to put exchangeable data in. And I also need an algorithm that doesn't distinguish between the data points, because if the algorithm had an autoregressive term in it, even if the data going in was IID, the residuals coming out would not be exchangeable because the data would be treated in an ordered way by that model fitting process. So I need the input to be exchangeable, and I need the sort of algorithm modeling step to keep that, to preserve that exchangeability. So in a picture, why do I need this? It's because of this argument here for like informal proof of why conformal works. So on the left-hand side, I have my XY data. The color coding from light to dark is indicating I equals 1 for the lightest through I equals n plus 1. So like the ordering of the data. And here the data is IID, so there's no pattern to where light blue and dark blue appears in the picture. I've circled the test point, it's the darkest blue. Now this line here is just the least squares line. And now the question is that if I can see the left-hand plot, but all I show you is the right-hand plot, so the right-hand plot shows you the data, but without its index, like you don't know which one is I equals 1. And it also shows you the fitted model. But again, the fitted model is just least squares. So that doesn't tell you anything about the order of the data points because least squares doesn't care. Can you tell me which one is the test point? Like which one is the circled one? And if all you see is the picture on the right, all you can tell me is that it's equally likely to be any one of the black dots. And that's what conformal prediction needs. It needs exchangeability of all of the data, meaning that the test point could come anywhere from the empirical data distribution, even after you see the line. Okay, now what happens in practical settings? We might have two challenges coming from these two assumptions, one or the other or both being violated. First is that maybe distribution drifts, or maybe you have dependence. And so perhaps the data is like similar to an exchangeable distribution, but not exactly exchangeable. The second challenge is that we might actually want to use a non-symmetric algorithm. So why would the second one come up? Because this sounds like, okay, the algorithm is under my control. If I know that conformal needs a symmetric algorithm, I just use a symmetric algorithm. The problem is that we want conformal to not just give validity, we want it to be able to give prediction intervals that on the one hand are assumption-free valid, but on the other hand compete with state-of-the-art methods. And if state-of-the-art methods use an autoregressive model or something else that that implies a non-symmetric treatment of the data, so like I downweight past data points that were long ago because the distribution might change over time, then for conformal to be competitive with that, we need to allow it to use a non-symmetric algorithm. But now let's look at our picture and we'll see how violating one of these assumptions or the other assumption will create a problem with this sort of proof technique. So first, let's say we have distribution drift. So you can see on the left-hand side, the light blue points are more in the top left corner, the dark blue points are more in the bottom right. If I show you the picture on the right, can you tell me where the test point is? Well, if you know that distribution drift happened, then the least squares line tells you nothing because it doesn't reveal the order of the data. But you know that the test point is the most recent data point, and you know that distribution drift happened. So that means that you know the points towards the bottom right of the plot are more likely to be the test point. Your belief is no longer just a uniform draw over the empirical collection of data that you see. Now, on the flip side, maybe the data was IID or exchangeable, but for some reason, I chose to use a non-symmetric algorithm when I fitted the data and created my mu hat. So here's a picture of that. The light and dark blue is random because the data is actually IID, but the algorithm is weighted least squares, where my weight is high on the most recent data, low on the long ago data, meaning the darker blue points have the higher weight. Okay, so what does this mean? If I showed you the picture on the right, and if I hadn't shown you the line, then you would have no information about which point is the data point, is the test point because it's IID. But now I reveal the line to you. And you can ask, okay, could the test point be right here, this sort of outlier looking point for the line? And the answer is no, because if that were the test point, it would have been given the highest weight in that weighted least squares regression. And so that would have had to pull the line down. And so you actually have a ton of information. You could say like, this is definitely not the test point, whereas something that's really close to the line is quite likely to be the test point. So in this case, either one of these violations is sufficient to totally break the proof idea. And this is not just theoretical. conformal just will not work because fundamentally it only functions if the data and permutations of the data resemble each other. Okay, so now when we started thinking about this problem of like how to allow these assumption violations and still have conformal work, we were really inspired by a talk that we saw last summer by Volk at the ICS workshop. So this was 2021. And he was looking at this electricity data set that tracks electricity demand in Australia, running conformal prediction to try to predict each time point. And his task was actually in this plot to show a violation of exchangeability. So I don't want to go into details of what he did here because it was a very different problem than what we were doing. The only thing you need to know is that this was something that would be a martingale if the data were exchangeable, so it should have stayed flat. But instead, on the log scale, it's going up into the 3000s. So in other words, this picture is very striking. It shows you do not have to go far to find real data that is blatantly not exchangeable. Obviously, we all know distribution drift is real, but here when like it was like e to the 3000, you know, the extent of that, of how much exchangeability is just totally violated in practice, was really, really striking to me. And so we're going to be looking at this data set in a couple of minutes for applying our method. Okay. So let's take a look under the hood of what's happening with how exchangeability plays a role for conformal, and could we modify that somehow in order to move beyond exchangeability. So when the data is exchangeable and the algorithm preserves that exchangeability by treating the data symmetrically, then what the picture showed us, now written in mathematical notation, is that the test point is a random draw from the empirical distribution of the training and test data. And so here we have the point mass of the ith data point, and we just add that up over all of the data points we observed. Now, of course, if the data is not exchangeable, this is not true, but is it possible that we could use like a weighted version of this, for example? So our idea is that if the assumptions are violated, we would like to say that kind of morally, we should be able to think of the test point as a draw from a weighted empirical distribution of the data. So intuitively, this feels right. Like, for example, if I have distribution drift, let me just say that recent data gets high weight and long ago data gets low weight. And then the test point is kind of like a draw from the empirical distribution that puts most of its weight on very recent data. So intuitively, that feels like it's exactly true. But to look at it mathematically, it actually turns out to work a little bit in an unexpected way. Okay, so mathematically, we'll come back to the challenges in a minute. Empirically, it works quite well as well. So here's a preview of our experiment on the electricity data set, the same one that was analyzed by Volk. And you can see that for conformal prediction that assumes exchangeability and heavily relies on it, there's a long period of time in the middle of the time range where the coverage goes down substantially. And then it kind of recovers, and actually it is too high for a while. Whereas the proposed method, which basically does exactly what I just described, put most of your weight on the recent past, its coverage kind of hovers around 90% the whole time. So it does what we think it should. So why is this working? What's happening in the theory? Okay, so when we tried to write it down, here's basically the challenge we run into. So I know this is a little technical. I don't know if this is of interest, but I'm going to attempt to show kind of why the theory falls apart. And please bear with me if this is a little dull. So basically, the idea is that in the full conformal proof, the reason that we think of the test point as a draw from the empirical distribution of the real data is because basically, here's the key step. If the data is sort of the same under any permutation, its distribution is the same under any permutation. The reason we say that the test residual has a 90% probability of being at the 90th percentile or below is because of this symmetry statement, which is whatever the probability is for the test point to be below the 90th percentile, it's the same probability for any other point to be below the 90th percentile. And only 90% of the points should be below the 90th percentile, only 10% should be above the 90th percentile. You get your answer in the end. So why is this statement true? It's because the event inside the probability is exactly the same on both sides of the equal sign, except I've permuted the indexing of the data. And if the data is exchangeable, and it's still exchangeable even after you pass it through some modeling process, because it's least squares and it treats it symmetrically, then permuting the indices shouldn't change the probability of the event. Okay, what goes wrong when we try to add weights? So first of all, the data might not be exchangeable, but let's not even worry about that yet. If the residuals are exchangeable, but I added in weight, here's the problem. This statement is no longer necessarily true because this is a function of the residuals on the left-hand side, and this is a function of the residuals on the right-hand side, but it is not true that I am applying the same function to a permuted vector of residuals. It's not the same event after permutation, it's just a different event. And the reason is that which one is on the left-hand side of the inequality, number n+1 versus number rk, has changed. But which weight I assign to which residual has not changed. And so there's no way to just permute the r's and see that this is the same event on both sides. They're just not. Now, on top of that, you might have non-exchangeability of the data, or you might have an algorithm that has some non-symmetric component to it. And so you have those problems as well. And so this is where the challenge comes in. But we know already that intuitively it feels like the right thing to do. And also the empirical results are promising. So let's see what we can do. Okay, so our aims basically are simple. Once we know what the two assumptions were, we want to relax them. We would like to allow for non-symmetric algorithms so that conformal can be competitive with state of the art, even in settings where a non-symmetric algorithm is the state of the art. And we also want to guarantee coverage. And we basically want the best of both. If exchangeability happens to be true, we don't want some approximate coverage guarantee. We want to do just as well as conformal and have an exact guarantee at finite n. On the other hand, if exchangeability is like only true-ish because the data has some drift, but it drifts slowly, we would like to know that we approximately get the right coverage level. Okay, so let me give our method in two different forms because it gets a little bit more complex once you have a non-symmetric algorithm. So first, this is the form if you still require yourself to use a symmetric algorithm for model fitting, but you want to protect against things like distribution drift, so you want to add some weights to the data. So this algorithm is exactly the same as conformal prediction with one modification, which is when I ask myself, is this value of y a value of y that I should keep? Like, is it maybe the right value of y? I compare the test residual to the weighted quantile of all of the residuals on the training point, where the weights come from some predefined weighting scheme. So if I have potential distribution drift over time, maybe I decay my weights moving back into time. If my data is instead gathered over some spatial grid, maybe I decay my weights as I move farther and farther away from the test point in the spatial domain. So this isn't necessarily time, although I'm kind of using that as a running example. Basically, high weight means that I trust this training point to be similar to the test data that I'm trying to predict. Low weight if I don't. Okay, so now let's go back to our pictures that we used to illustrate the problem, and let's see how this weighting scheme can help fix that problem. So the first assumption was I'm still using a symmetric algorithm, but maybe my distribution is not exactly exchangeable. Maybe there's distribution drift. So here's my distribution drift picture. And what we saw on the right-hand side initially was that that picture is not a good representation of what you know about the test point. The picture is implying that the test point could be anywhere in the training and test data, but actually you know it's more likely to be in the bottom right because of distribution drift. As soon as I add weight, now the picture is much more representative of your beliefs about where is the training point in this bag of, where's the test point in this bag of training and test data, because the weights reflect our understanding of recent data being more similar to the test point. Okay, second version, now we want to also allow ourselves to use a non-symmetric algorithm. So how come? Because using weights like already helps me fix validity. This is because I now want my intervals to be not just valid, but narrow. I want them to be accurate. So it turns out that if you want to use a non-symmetric algorithm, there's only one tiny modification of conformal prediction that you need, and then validity and distribution-free predictive coverage is guaranteed with just like it was before. And here's the modification, which is that when I run my algorithm here, when I run it on the combination of the training data that I observe and the test point, which I don't observe, but I guess its value of y, before I do that, I have to flip two data points. I choose a random position in the training data, and I take my test point and I switch those two data points, and then I run my algorithm. I want to point out that this isn't shuffling your data. If you're running something like a model that downweights the past, or an autoregressive model, or something that relies really heavily on the data being in a meaningful order, if you shuffled the data, using an order-based algorithm would be meaningless. But if you only mess up the order of 2 of the data points, almost all of the data is in its right order. And so a model that uses that ordering is still going to be fitted pretty well. Okay, as soon as we do that, then it turns out that this is kind of the only modification you need for conformal to now be allowed to use a non-symmetric algorithm. Okay, so this is just what I already said. This is very different and much more sensible than randomly shuffling the data. Of course, if I were to randomly shuffle the data, now I have a symmetric algorithm again, like stochastic gradient descent or something like that, which is symmetric in how it treats the data in sort of a distributional sense when you take into account the randomization. Okay, so now let's see why this sort of swapping trick fixes the other problem of where the non-symmetric algorithm reveals too much about the data. So this is the original picture where we illustrated the problem. Just to remind ourselves what the problem was, when we use weighted least squares and you look on the right-hand plot, you know that this point cannot be the test point because the test point gets the highest weight, and this point clearly did not get a high weight in the weighted least squares regression. But if we first do a swap, so this arrow tells me which point the test point got swapped with. Now I show you the picture on the right, and let's ask ourselves that same question. Could this be the test point? So you do know that that point didn't get a high weight in the regression, that's visible. But it still could be the test point. It could be the test point and then it just got swapped and therefore it got a low weight. And so of course this is very informal, but roughly speaking, what we're saying is that by swapping just one pair of points, we have effectively hidden where the test point is among the pool of data. Okay, now I'm not going to go into it, but you can also define non-exchangeable versions of split conformal and of the cross-validation style methods like jackknife plus. But I want to move on because I know there's not much time left. Let me show you quickly some empirical results that tell us how well this is letting us move beyond those assumptions, and then I'll go into some theory if there's some time remaining. So the methods we're comparing are regular conformal, weighted non-exchangeable conformal, and finally weighted non-exchangeable conformal with a non-symmetric algorithm. So the algorithms they're using are least squares as a symmetric algorithm and weighted least squares as a non-symmetric algorithm. Okay, so first some simulations. If I have IID data, everything performs just fine and they're pretty much indistinguishable. If I have change points or distribution drift, then exchangeability is violated. And what you can see is that blue, regular conformal, loses coverage much more severely than the non-exchangeable weighted conformal, which uses weights to compensate for the distribution drift and to quickly recover from change points. Now on the right-hand side is the width of the interval. What you can see is that non-exchangeable conformal could be very wide if you're still forcing yourself to use a symmetric algorithm, that's yellow, but it's much, much more precise and narrow if you allow yourself to use a non-symmetric algorithm in red. Now back to the electricity data, the top 2 plots are for the real data. What you can see again is that non-exchangeable in red and yellow maintains coverage a lot more than full conformal. And on the right-hand side for the prediction interval width, we can see that using weighted least squares does give us a little bit of an improvement in terms of the precision. On the bottom, what we did is we said, okay, well, real data is problematic in many ways. Its distribution is very complicated. And in particular, it might have distribution drift. What if we just remove that last thing? So what we did is we randomly shuffled the data, but the data is still the same, like it's still heavy-tailed or whatever. But now it's exchangeable because it was randomly shuffled. Now we see that everything has coverage. And on average, it's roughly the same width, although weighted conformal has a much lower effective sample size, so it's a little more jumpy. So we can really see that it's non-exchangeability specifically that causes a problem in the top plot for regular conformal and where non-exchangeable conformal can help. Okay, I'm guessing there's a question in the chat, so let me take a look. Okay, instead of swapping the test point with a random point, could we instead insert the test point in a random place in the list without altering the relative positions of the other points? That's a great question. So our theory would look very different, and we'll see why in a minute. In practice, I imagine that would probably behave very similarly. Yeah, Yeah, I think you could probably have an analogous version of our theory, and that's a really good suggestion. That would be another interesting way to look at it. We've considered different versions of that for time series type settings where you think about sort of like taking blocks or rotating or something like that. So definitely the pairwise swap is maybe only one of like a range of possible ways of perturbing the data. Thanks for the question. Okay. So all right, so that was the like 2-second view of the empirical. Yeah. Uh-huh.
So for biological teaching, for example, when you look at the differences of the data points and the consequences of changes.
So it's true that you can do a little bit of processing on a time series, like taking differences or ratios, perhaps in other settings, and you are much closer to something that's exchangeable. That's very true. We were using this as an illustration of what you could do when you really cannot get to something that's very exchangeable. I suspect on this particular data set, even the differences would still suffer some of these problems. And the reason is that we investigated why the blue is so, it's not just that it's always low, it's like fine, low, fine. And the reason is that in the middle time range, it appears that the response is much more noisy and unpredictable, at least around any of the simple models that we tried. Like if you just train the whole thing on a batch, like from the future, right? You have all your data, the residuals for the middle time range are just much higher. And so I suspect that there's just more noise for some reason during that period of time. And so I don't know if those differences would still be more noisy than the differences like early in time. So maybe that's getting too specific here. In general, for a time series, I agree with you that taking differences or doing some kind of pre-processing to get you much closer to exchangeability would improve the performance of all of these methods a ton, whether you're using conformal or you're using the new version of conformal. Yes.
So I'm just confused why this swapping one point was completely like randomized, I guess, on that example that you showed. Because we still know it's just one point, right?
It's
So
just
there's
one
like-
point, but it could be any point. Like imagine that you pick where it goes at random. The data is no longer exchangeable, but you don't actually need exchangeability for conformal to work. You just need it to be true that the test point is equally likely to be any of these points, right? So if I put it in any position uniformly at random, then by definition, it's equally likely to be any of those points. And we use a weighted version of that, but the analogy just kind of follows. So you're very right that it's no longer sort of permutation and variance, but the trick is that you don't actually need that. You only need to ask where is the test point.
On the issue of weighting, it seems to me that you can have an arbitrary number of weighting things that will all give you validity, but they might have widely different efficiency.
You're absolutely right, and we do not know how to deal with that. Basically, like whether you can do cross-validation or whatever, we haven't gotten that far yet. Yeah, choosing the weighting scheme is a huge open problem. Yeah. Okay, so here's what our theory says, and then we'll take like a maybe 60-second peek at the proof. The theory says that as long as you choose your weights ahead of time, so that's another open question as to whether that's the right way to do it. Your coverage is at least 1 minus alpha minus something that looks at how non-exchangeable is the data. So here what we're saying is that if I take my data versus if I take my data and I swap the ith training point with the test point, so just those two pairs move, can I tell the difference distributionally between those two versions of the data set? Now, of course, if the data is exchangeable, permuting it doesn't change anything, and this distance is 0. But if the data has some drift, maybe this distance is small if I is really close to test time, or large really long ago. That's where the weights come in. What you want to do is pick the weights to be high anytime you think this distance will be low, like for recent indices I, and vice versa, you want this low anytime this is high. I also want to point out that this is not actually a distance between data distributions. It's only a distance between the distribution of the residuals you get when you model that data. So that actually could be a lot better because data could be high dimensional, but residuals are low dimensional. Okay, some implications. If the data is actually exchangeable, you lose nothing. What this means is that we didn't previously know you could use conformal in combination with non-symmetric algorithms. Now we know that as long as you do a pairwise swap, it doesn't lose coverage. If the data is independent, you have this much more interpretable lower bound. We're just looking at total variation distance between the test distribution and the ith training point distribution. We can also see that these, the symmetric case is a special case. So these apply whether you're using a symmetric or a non-symmetric algorithm, as long as for the non-symmetric algorithm, you swap. For the symmetric algorithm, swapping doesn't matter. If I shuffle my data and then feed it to least squares, I'll still get the same answer. Okay, so extremely fast overview of the proof. So what is actually happening? Imagine that I swap my data, so test point, training point, swap, and x tilde, y tilde is my swapped data. Now I run a regression on this data, I get all of my residuals, but of course, any one of those could be the test point because the swap kind of hides it in that vector. Okay, so the question is, where is it? So what's the probability that the test point is hiding at the ith location, given that you can see those residuals? If that probability is exactly equal to the weighting scheme I used, so like if I chose my swap uniformly at random, those weights are uniform weights, then the weighted quantile or unweighted quantile, if the weights are uniform, that I compute to construct the method is exactly the right distribution for coverage. Now, the problem is that if the data has some drift, then you actually might be able to find the test point, because why is there a data point that looks like current data hidden way in the distant past? Probably it's the test point. It doesn't look like it belongs there. So basically, all I have to do is compare this distribution, where's my test point, given the residuals, after planting the test point somewhere in those residuals, with what it would look like if everything were exchangeable. And so that's where this total variation calculation comes in. I don't want to go over time, so I'll just stop there. Okay, so just to summarize, we can use weights to give us robustness against non-exchangeability. We can use the swap trick to give us kind of immunity against a non-symmetric algorithm. In combination, what that means is that it now makes sense to apply conformal and still get theoretical guarantees in a broader range of settings. Settings where you have distribution drift, settings where you want to treat the data in an ordered way. Under the hood for all of that is a new proof technique that, to me, uncovered a lot of intuition for myself about like how conformal really works, looking at it from a totally different perspective. And so we hope that this might be able to also potentially give some insights for future developments as well. And we're really excited about potential like applied future directions, as well as more theory that could be done in this direction. Okay, so some open questions, which most of you guys have posed already. How do we pick the weights in a way that's optimal for the data? Can we do it in a data dependent way? And can we use this to try to help us compare multiple models or other more sophisticated questions? All right, so I'll stop there. Thank you all very much. And I'd be very happy to take questions and hear your ideas. Thanks.
Do we have one question in the audience?
Just remind you, there will be a reception for Rina 4:15. Yes, and 2:15. Go ahead. Okay.
So thank you very much for the interesting talk. So my question is that, so usually when we talk about the condition interval, we have a different models. We would like to use the condition interval to classify the, maybe to select some model. Now the thing is that, okay, even the model is wrong, you can still get the critical coverage rate for the prediction interval. And my question is, for this, if the model is correct and model is wrong, which one will give the better prediction interval?
Yeah, so this is a great question. We thought a lot about like, how can you do this to combine models, to compare models and questions like that. And to some extent, this is really something that is complicated and there's not a ton of work that I'm aware of yet on that question. But I don't know if this is exactly the same, but a related question is, if you do have like the right model versus a very bad model, what does this give you? So there are quite a lot of very precise results about that. And basically what the flavor of those results is that this is valid if your model is right or wrong. But if your model is right, we would like to know that this is not more conservative than the sort of assumption-based method, right? So like, let's say I use least squares and the parametric interval would have been just fine because the assumptions are true. So in this case, it really depends on what score you're using. So if your model is correct for like mu hat really is consistent for the mean of y given x, but the variance of y given x is not constant, if the score you use leads you to intervals of the form prediction plus or minus constant margin of error, it still cannot be optimal. So you actually kind of need optimality of like the entire modeling and error measuring procedure. So one way to quantify that is to basically just say, like, is the oracle prediction interval in the family of the sort of family of like the shape of prediction interval that you could get out of this procedure? And if so, like then consistency of the base algorithm A for giving you the right model will mean that the output of conformal is going to converge to the oracle output. There's other results I mentioned earlier when I talked about different scores that you can do what's called distributional conformal prediction, where you estimate the either the CDF or the density of Y given X. If those estimates are consistent and you build conformal around those rather than the like mu hat plus or minus construction, then again, you would get convergence to some kind of oracle. So there's results along those lines of like, if your model happens to be right, then what do you get? But the question of like, how do you use this to check if your model might have been right? Or how do you use this to compare models or pool models, some of which might be right? That's something that I think is still a really open area of research. Thanks.
All right. Thank you. I think we are over time, so we'll finish here. So next week we have the Pillai Memorial Lecture, which will be delivered by Dr. Alan Gelfand from Duke University. And again, we have a reception at 4:15 at Math 215. Thank you everyone.